go ahead and get started here. So we're talking about wave behavior. So there's a couple of things that can happen, and again, this is going to be kind of a heavy definition-based set of notes. If you know these terms, great. If not, then you should probably copy down a definition or two for yourself. So, if we have waves and they travel through media, and we talked about that last time, when the wave reaches the end of the media, let's say that you're talking using a sound wave, and that sound wave goes out through the air in here. Well, the air is the media, right? But the sound wave can reach that wall, right? And we go, okay, well, what happens when that sound wave reaches the wall, or any wave? Well, it has two options. Essentially, it can reflect or it can transmit. So reflect means to bounce, as you see in the picture, and transmit means it's going to pass through. So those are the two definitions. So reflect is bouncing, transmit is passing through. So if I talk, some of the sound waves will bounce off the wall and some will pass through into the wall, possibly out of the wall to the other side. When a wave goes from one media to another, we call that transmission. But when it's transmitted, the wave will do a thing called refract. And that's the picture, the second picture you see up there. The wave will refract simply because it's going from one media to the other. So remember what we talked about last time. The speed of the wave is determined by the medium. If the wave is going from, say, air to the wall, it's going to change media, so therefore it's going to change speed. Now in the case of going from air to the wall, it's going to speed up. Like sound waves will travel faster in the wall than they will in the air. Because it's speeding up, it's going to end up bending, and that's what refraction is. It's the bending of a wave when it's going from one media to another. And the reason why it bends is pretty easily seen if we have the right image. So right now I'm just going to tell you that refraction is the bending of a wave when it goes from one media to another. And here today we'll look at a demo that will show us exactly why that wave bends. But keep in mind it has to do all with the fact that wave speed is determined by the medium, and because it's changing medium, it's going to change speed. Okay. So here, there's not much on this slide. This is just reflection and refraction of sound waves. You can kind of think of the first image was light waves, this one's sound waves. It happens with all waves, but it's obviously going to be harder to see with sound waves because you can't see sound. But here just kind of gives you the same thing that, like, if I'm talking, the sound waves can bounce off the wall. Matter of fact, that's what you guys are hearing on this microphone, is you're not just hearing me speak, you're hearing the sound bounce off these walls and come into the microphone as well. You're hearing these echoes and reflections. It's called reverberation. It's one of the things that makes it sound a particular way when you're in a particular room because of the sound waves bouncing off and so on. When waves hit a boundary, they have, again, they can reflect or they can transmit. And so if we're thinking about like a traditional transverse wave, like light, what happens is if it transmits, everything stays the same. So like a crest transmits as a crest, a compression transmits as a compression, and so on. And so that's what you're seeing here in this upper picture. This crest becomes a crest when it goes into the thicker piece of the rope. It's a different medium. But you can always get a reflection. Okay, so here you can see this reflection comes back. And when things reflect, they reflect opposite. So a crest becomes a trough, and a compression would become a refaction, rarefaction, not refraction, a rarefaction. And so that's what you're seeing there. Now what's interesting is that the wave will always have some of it reflected, but some of it will always, not necessarily always transmit. So you always get at least a little bit of a reflection when waves hit a boundary. Sometimes it's all reflected, but sometimes it's transmitted. And so usually you get both. You get both a reflection and a transmission. But If nothing else, then you get just a reflection. There's no way to get just a transmission. What's interesting about that is, for example, if you've ever looked inside of a car, like, if you go outside, probably not today because it's kind of rainy, but if you went outside on a nice sunny day and you looked into somebody's car, you would be able to see through the window down, and you could see the seats of the car. Well, that means the light had to transmit or pass through that window for you to see. Okay, that's transmission. But usually when you do that, you should also be able to see on the window your reflection, because the light is also bouncing off and coming back to your eye. And so that's an example of being able to see both a transmission and a reflection. So here, this talks about, again, waves changing media, but it turns out it doesn't have to be just going from air to the wall. That's obviously a different media. But you could have, say, the air going from just hotter air to colder air. That's true, Brendan. I'm just staring into their car. What are you doing? So here, the waves at boundaries, it talks about that, like, the temperature of the air will actually be a different media, because again, the media dictates the speed. And if the air is, let's say, a lot hotter here, as the wave comes in, it will essentially act like that's a different media, and it will change speed when it's in this new media. So here it gives you some lists. It says, okay, in air, the temperature really affects the speed the most. In water, the depth affects the speed. In solids, how rigid it is, or the rigidity of the structure affects how fast it goes. So if you don't know what rigidity means, think like Jell-O. Jell-O is not very rigid. So most solids, the more rigid they are, like your chair is pretty rigid, pretty solid. And so what's interesting about this is you go, okay, sure, it changes speed. But even if you think about temperature of air, the air, if you were to look at the equation for this, you would see that it has to be a really large change in temperature of air for the airspeed to be significantly affected. Like the speed of sound in air is like 330 at 0 degrees Celsius, or 32 Fahrenheit. But at like 100 degrees Fahrenheit, or 100 degrees Celsius, or 212 Fahrenheit, like the boiling temperature of water, the speed of sound is only like 360 or something meters per second. Like it's gone up, sure, but it hasn't gone up that much. And so you go, okay, yeah, it changes a little bit, but it turns out these small changes actually explain a few things that you guys have seen. So you guys have probably been outside during a Texas summer, and if not, I'm sure you will. You guys notice it's kind of hot, but have you ever been outside in the summertime? You look down the road, it's super hot outside. You look down the road and you see what appears to be water down there. You ever done that? I remember as a kid, I would see this water sitting down there, and I'd be like, it's like 100 degrees outside. There's no way there's water just sitting down there. And I would go and walk towards it, and guess what? There was no water there. But if I paid attention, you would actually see this puddle of water not stay there, but as you walk towards it, it would actually stay about the same distance from you. Because what that is, that's actually a mirage, okay? And what's happening there is essentially you have blue sky up here, and the light from the sun or whatever is hitting this piece of sky, scattering off of it, and you're seeing it. Okay, blue sky is right here. But some of that light from that piece of blue sky will go down and just strike the ground somewhere in front of you. Well, what's happening is because it's so hot, and like the surface of the road or sidewalk is so dang hot from the sun, it might be 100 degrees in the air, but it might be 120, 130 on that street or sidewalk. And so it heats that air right above the sidewalk really hot. And so what happens is that light from the air will come down, and instead of coming down in a straight line, it will refract, or it will bend, and it will come back up towards your eye. And your brain will see this bluish sort of stuff, but it thinks it came from over there. And so it goes, oh, that blue stuff is sitting over there on the ground. And of course, if you see kind of bluish stuff sitting on the ground, you think it's water. But again, it's just a mirage, and it's actually the refraction of the light rays being bent up towards you. And so that's the important thing here to note, is that these things change speed, based on air temperature or the depth of the water. And it's not a huge change, but it's enough, and whenever that changes, it will bend or refract these waves. So if you click here, this actually takes you to a PhET sim, and in this PhET sim here, you can simulate some waves here, so I can like shake this up and down. Here I'm going to switch to the pulse view, and so this is the amplitude. So notice amplitude is how far up and down it goes, okay? So if I move it to here, well, that's too far. Move to here, just boop, get a little pulse, and there it goes. So amplitude is how far up or down it goes, which is what we talked about last class. Now how fast this moves, like the actual speed, depends on the medium, and I can change the medium by changing the tension here. Like if I hit it with low, you'll notice that I'm going to keep this amplitude high. It just takes a while to get down there. Now you should also notice that the amplitude decreases as it goes because there's some friction, or as it says here, dampening, that will take away your energy. And the height of your amplitude, that is your energy. And so I can do, 1, 2 pulses here, and they can travel on down. They'll hit the end. And as we just discussed, they'll reflect, upside down, and here they come back. So I encourage you guys to play around with this. You can change the pulse width, you can bust out these rulers and stuff and measure things like, wavelength and all that. It's a very useful simulation. All right, so let's talk about waves in 2 dimensions. Because when we talk about, reflection and refraction, it's kind of hard to see what's going on unless we look at least 2 dimensions, because it's going to come down, bounce off. And the same thing applies in 3 dimensions. So here, I'm not going to spend a whole lot of time on this slide. I will spend some time with this demo here in a second. But on this slide, it's essentially trying to define incident ray, reflected ray, refracted ray, the normal, and then all of these angles. And I know that this seems like a lot, but really what you guys need is just the definitions of these things so that I can have this discussion with you. So, first of all, we have the normal, this dashed line here, moving up and down. It says right here, normal is a line perpendicular to the barrier. So here's the barrier between my 2 media, so let's say it's air and maybe water. This line is perpendicular to the surface. So if you guys don't remember, way back, probably October, November, we talked about Newton's laws and we talked about forces. And there was a particular type of force that was called the normal force. And we called it the normal force because the word normal means perpendicular. All right? So it's the same thing here. It's normal, it's perpendicular to the surface, right? That means 90 degrees between this thing and the surface. Here on this next slide, it actually gives us the definitions of incident, reflected, refracted, and all of these angles. So these are essentially the same thing here. But like I said, if you know what these things are, you don't need these definitions. If you don't know what they are, you need the definitions. So the incident ray is going to be the incoming wave. Now it's an actual wave, but we're looking at it in terms of what are called ray diagrams. It's essentially simplifying it, and we're not looking at the wave pieces. I'll show you in this demo what it looks like to look at it from a waves perspective, and you'll see how that actually makes some sense, especially when it comes to refraction. So the incident ray is the thing that starts everything. So you can imagine, like this is a ball, a wave, or whatever. If you throw a ball against the ground, it will bounce up. Well, if you were to measure this angle, we use this normal here, and we measure this angle. So this angle right here between the incident ray and the normal is the angle of incidence, right here. And then this angle here between the normal and the reflected ray is the angle of reflection. And likewise, as we saw in the last diagram, the normal should come down here and give us a refracted ray down here. So first off, we have the law of reflection, which is very, very easy. The law of reflection says the angle of incidence will equal the angle of reflection. That's it. So if I was to give you an audit, and I asked you a question, I said, hey, this light ray comes in at 90 degrees, or not 90 degrees, like 20 degrees, and it bounces out. What angle does it bounce out at? Well, I'm asking for the reflected angle. If it comes in at 20, it comes out at 20. Okay? If it comes in at 30, it bounces out at 30. And this happens for waves, but it also happens for physical matter. This should be very similar to you guys. They're like, if I throw a ball down at 20 degrees, it bounces out the exact same angle. This is exactly what you should expect if you're throwing a ball. And so the law of reflection says that this angle equals that angle, that these things will always be the same, okay? So very simple. Now, there is a law that talks about how we calculate the angle of refraction from the angle of incidence, and it's called Snell's law. We're not going to cover that. And it has nothing to do with anything other than there's just no need to cover that. It's just a bunch of math that we don't need to do. But let me talk about why refraction occurs. The reason why refraction occurs is right here. So here I've got my little laser here, and I can shine a laser down onto the surface. And so we can have our incident ray, we have a reflected ray, and we have a refracted ray here. So, and I can do any of these things. But to prove the angle, the law of reflection, I need some way of measuring the angles. So here I set this up, that's pretty close. And so you'll notice if I send it in at 0, it comes out at 0. So the reflected comes out at 0, so it goes right back to my laser. And then the refracted goes straight through as 0. So 0 is always 0. Cool. But if I take this laser here and I move it to, say, 30 degrees, you'll notice that the angle of incidence between the normal and the incident ray is 30 degrees. It will hit the surface and reflect out at, well, 30 degrees. So the angle of reflection is, well, 0 to 30 degrees. And then down here you can see the angle of refraction. Now the angle of refraction, you'll notice, is not 30 degrees. In this case it's less than 30. Matter of fact, it'll always be less than whatever angle I put it in at. So 60 in, 60 reflected, but less than 60 refracted. And that has to do with, well, just how different the two media are. So I've been promising you to explain exactly why refraction happens. Well, it makes a lot of sense, not so much if you look at light or sound waves as a ray, but if you look at them as a wave. And so what you're seeing here is you're seeing like crests and troughs. So think about this three-dimensionally, like you're looking top down. It's like these red lines, let's say, are crests, and the black lines in between are troughs. So you're seeing crest, trough, crest, trough, crest, trough. The first thing you should notice is that when they go from here to there, they get bunched up. So in this case, it's going from, say, air to water. So in the case of a light ray, it's going to travel slower in water. So if this represents, let's say, red light, the light ray will actually go slower in water. And the reason for that is, well, the water molecules are closer together and the light doesn't want to interact with them, but it has to. So here you'll notice that because it's moving slower, do you see how these guys are actually closer together than these guys? So one of the things that happens is when you change from one media to another, the speed has to change. Frequency doesn't change. Frequency stays constant. Like it's red up here, it'll be red down there. Frequency is the number of waves per second. That doesn't change. But do you see how much closer they are together? It changes the wavelength, okay? So why does refraction happen? Well, if I bend this thing at an angle, you guys can really see what's happening. So if this thing comes in, because the wave does have a width, I mean, granted, it might be a tiny width, but it has a width. Okay, and if you look at this, like think about like pushing a lawnmower on concrete or like pushing a skateboard, something that has like an axle. So if you think about the skateboard going along, most of you realize that it's easier to ride a skateboard on the sidewalk than on the grass. So instead of thinking of this as air and water, think of this as like the sidewalk and the grass. So if you're riding your skateboard, you're probably going to ride on the sidewalk. Well, if you decide to go into the grass, accidentally or on purpose, and you come in at this angle where you're just going to go straight in. So as soon as you hit that grass, boom, you're going to slow down, okay? But if you come in at an angle, what happens is the wave or the wheels, the front axle of your skateboard, one wheel will hit the grass before the other wheel. And as a result, that first wheel will slow down more than the other one because it's still on the concrete. And since that first wheel slows down and the second one's still going, it's actually going to cause it to turn. So let me say that again. As this thing comes in, part of the wave will hit first and will slow down first. Because if this is a physically connected object, if one side of your body has to slow down and the other part doesn't, it will cause you to turn. Okay? Now in this case, we're going from less dense to more dense, so it actually turns like this. Like whichever side hits first, it's going to slow down first, and it's going to turn that way. But what's interesting here is if I switch this let's say I put water on top and put air on the bottom, you'll notice that the same thing happens, but it actually turns away, because if you're riding a skateboard in grass at an angle like this, well, again, one wheel will get out before the other one, and since this one's able to roll faster, it will bend, in this case, away from the normal. So hopefully that makes some sense, but again, you have to think about something that has an axle, and like, if part of that axle hits first, well then it's going to slow down or speed up accordingly. All right, so that is essentially what happens when waves hit a physical thing, like the medium. They can either transmit into the next medium or reflect, and if they reflect, nice and easy. If they transmit, then there will be some refraction or bending of the wave that will occur. So now let's look at what happens when waves hit each other. Now this is the most unexpected thing. When waves hit each other, they have a thing called superposition. This is something matter cannot do. It's a matter of fact, if you can make something do this, that's what proves that it's a wave. It has this property of superposition, because if I take a ball and I throw it at my desk, it's going to bounce. It reflects. That's it. That's its only option. At best, if I shoot it really, really hard, it will just plow a hole right through my desk. But not so with waves. If I throw a wave at my desk, it could bounce off, but it could also pass through to the other side. Which is why you can, even though people are, say, talking in a closed room, you can put your ear up to the door and you can listen, because the wave is transmitting through the door. Waves can be in the same place as a piece of matter. But matter of fact, waves can be in the same place as another wave. So superposition is given like these pictures here. But before we get to those pictures, it's not even that complicated. Think about it like this. If you're sitting there at school or at home, and you've got a light, let's say the lights from the ceiling are shining down on your desk, lighting it up. Okay. Well, you go, okay, the light from here is making this brighter. Makes sense. Well, if you took a flashlight and turned it on, that's on. If you turn this flashlight on, it will also light up the desk. What happens on your desk? Well, it just gets brighter. The two pieces of light coming from my flashlight and coming from the ceiling don't care that this is coming from a different source. They just simply add up and they make your desk brighter. That is superposition. If I have a ball sitting on my desk and I put another ball on top of it, does it just sit there? No, they're going to like hit off of each other, they're going to roll away or whatever. They don't want to be in the same place at the same time. So superposition is that the waves can be in the same place, the exact same place at the exact same time. So what happens? So let's see here. If we're looking at these pictures here we have a little crest and a big crest. And you'll see in this first picture they're coming towards each other, right? Here they're getting closer. When they're on top of each other, they just add up. They just make a bigger crest. And then, again, probably unexpectedly, they don't bounce off of each other. They pass through each other. Okay? That's not what happens. If I throw a ball at another ball, they bounce off. But if I throw a wave at another wave, they just pass right through each other. They don't care. They just... And the result of what you see when they're in the same place at the same time, the superposition, we call this interference. Okay? And the interference can take two forms, constructive interference or destructive interference. And so here in the second figure, you can see we have a crest and a much bigger trough. Again, they're coming towards each other. They superimpose and interfere, and then they pass through. Right? They pass through. They do not bounce off. So here, this slide just simply shows constructive interference. But again, waves are energy that's traveling. So just showing a picture is not great. This is why this moving image is a lot better. So again, it shows two wave crests coming towards each other, making a large thing. This is constructive interference. So it says there an example of constructive interference is a tsunami. And that's the thing about tsunamis. They're typically triggered by earthquakes. And most earthquakes do not lead to a tsunami. But it's hard to predict because these waves will come out, reflect off of, say, like mountain ranges or other things in the ocean, and they can come back together to superimpose to make a much larger wave. And that's when they can be really devastating. The next slide here is talking about destructive interference. And so here we have a crest and a trough. In this case, they're the same size, so they just cancel out in the middle. So again, that's destructive interference. A great example of this is actually noise canceling headphones, which a lot of you guys have. And the way noise canceling headphones work is they have a microphone on the outside, and when it picks up sound from the outside, it takes that sound, it processes it, and it replays almost the exact same sound to your ears. But the reason why it sounds quieter is because they play it, well, exactly as you're seeing here, just out of phase so that it cancels out the sounds from the outside. And that's how noise canceling headphones work. They actually work by playing more, quote, I wouldn't say music, but more noise. But they're playing it just opposite of the wave that's already out there to cancel it out. These last couple of slides are talking about, again, just wave interference and superposition. Now the thing is when you're looking at these waves interfering with each other, it can be really hard to tell what's going on, because here I'm giving you a bunch of pictures, and I give you more pictures of constructive and destructive interference. But here it also defines things called nodes and antinodes. So the first thing I'm going to tell you is node means no vibration. So node means no vibration. Antinode, well, anti means not, so antinode means not no vibration, or maximum vibration. So if we go back to this waves on a string that I showed you guys earlier, I can go to this thing where it'll oscillate, okay? So here it's putting these waves in. You'll notice they're getting smaller as they go down, and now we're getting some interference as they come back. So let me let it go for a second here. I think it's about done. That's not great. Oh, that's pretty good. So here what you're seeing, what I'm trying to show you guys, is a standing wave. And so what you can see is, like, just focus on this end piece. You see how it goes crest, trough, crest, trough, crest, trough, crest, trough. You see how this thing is not moving at all? This green dot's pretty close to not moving, not exactly, but what we're seeing here is the same pattern repeating over and over and over again. This is called a standing wave. And what's happening here is that if you, like I said, just kind of focus on this end piece, you can see that, like, if I said, hey, looking at this end piece, is this a crest or a trough? Well, it kind of depends on when, right? If I pause it, well, that's not a very good pause. There we go. So now I got a crest, right? Here, I'm going to slow it down. So crest, and then a trough. Okay, I got a trough here. So now it's a trough. But if I was to ask you, is that a crest or a trough while it's playing, like at full speed? Like, that doesn't make any sense, because it's like, well, it's kind of both. So how do we address that? Well, when we see these things, these patterns, these interference patterns, we don't call them crests and troughs anymore. What we tend to call them is nodes and antinodes. So a node is a point of no vibration, like that green dot that was in the clamp. That would be a node. An antinode is where you have that crest and the trough just kind of trading back and forth. And it could be, you know, a compression and rarefaction trading back and forth. But nodes and antinodes just mean node means no vibration, antinode means, well, not no vibration, or maximum vibration. And so again, we're going to use those terms instead of just regular, you know, crest and trough, because, like I said, it's kind of hard to see if they're moving. When these things interfere with each other and create these standing waves, they give off what are called harmonics, okay? And they appear to stand still due to interference at just the right frequency. So an example of what I mean by that is that if you take a string and you, like, pluck a string, it will vibrate and have a bunch of waves that go out, hit the ends, come back. But overall, it will make a particular noise. And we call that, like, the harmonic that you're listening to. And what a harmonic is imagine you have that string here, is it has several modes that it can vibrate in. Like, the whole string could go back and forth, like you see this top one here. Or you could pluck it and this goes back and forth like this, right? And we call this top one's called the fundamental, this one's called the first harmonic, second harmonic, third harmonic, so on and so forth. But this is what would happen with a string, because it's fixed at both ends. And so when you just pluck a random string, it could do any one of these. Usually it's a combination of these things that it's vibrating in. but it's usually happening so fast you can't see it, but you can usually hear it, right? We're not going to get too deep into this, but what I want you guys to realize is that when things vibrate, even when somebody sings or plays an instrument, they're creating these waves, and they'll be set up to create these standing waves, and the standing waves is what you're hearing, especially in terms of music. So these standing waves are what we have fundamentals and harmonics. So fundamental is simply the lowest wave, standing wave you can make there. And all of the harmonics are mathematically related. Like this fundamental will have a particular frequency. Let's say it's 10 hertz. Okay, well that'll be lower than you can hear, but maybe that's the fundamental for your string. Well, it turns out you can get to the first harmonic by going twice as fast. Like this would be 20 hertz. And the third harmonic would be, well, 3 times your fundamental, which would be 30. And then 4 times your fundamental, which would be 40, and so on. Now, whether or not that's the fundamental frequency depends on A, the length of the string, and B, what the string's made out of, like the thickness of the string, essentially. And the same thing can happen for, wind instruments and, like I said, people singing. We'll talk more about that when we get to actual sound. But anything can have these waves and harmonics go through it. So, like if you hit something, it will have a particular noise because it has these waves traveling through it. This video here, which again, I'm not going to play because I don't want to play over the internet. If you watch that video, it shows you waves traveling through a baseball bat when it's hit with a baseball, which you may not have thought that occurred. But one of the really interesting things is if you guys have ever played a sport, not just baseball, but like tennis, hockey, something where you hit something with a stick, you can always kind of feel it in your hand when you hit something, but what a lot of people don't realize is what's happening is, let's take the baseball example. Okay, you're going to swing your bat at the ball. So the ball's coming in opposite direction of your bat, and you're like, I knock it out of there. Well, what's interesting is that if you just hit it just anywhere, yeah, you'll probably hit the ball away because you bat and you have more momentum. But most of you guys know, especially if you've ever played with sports, is there's a particular spot on that bat that you want to hit it. Same with a tennis racket, same with your hockey stick. There's a spot that you want to hit, and typically it's called like the sweet spot. And the reason why that sweet spot exists is because when that baseball hits the bat, a wave of vibrations will travel down the bat to the handle and then travel back, and it will set up essentially a standing wave, like one of these things. And that standing wave, where that sweet spot is going to be where you have one of these big fat antinodes, right? So node is no vibration, antinode is going to be maximum vibration. So you're going to have that maximum vibration in the bat right at the sweet spot. And so what's literally happening is the ball comes in with a certain amount of energy, and you have a certain amount of energy that you're trying to transfer to it with the bat. But because that ball has so much energy when it comes in, it creates this wave in the bat that travels down, comes back, and will actually amplify your swing. And so what ends up happening is when you hit that thing right at the sweet spot, it travels so much further. And a lot of people don't understand that other than, yeah, you hit it at the sweet spot. But what's literally happening there is the energy of the ball is going into the bat, creating this wave, and you're actually reflecting that energy back out and using it to propel the ball forward. So when you hit at the sweet spot, you are using the ball's own energy to push it back, which is why it goes so much further, because it's not just your energy you're bringing in, but with your skill, if you're able to hit it right in the right spot, you can actually use that energy to push it back out. Now, this particular video here is actually about hitting the ball in the wrong spot on the bat. And if you do that, the energy of the ball can be large enough to shatter or fracture the bat itself. So, that's what the video is. This slide and the next slide talk about diffraction, and this is different than refraction. So we talked about reflection, bouncing. Refraction, it bends because the wave is going from one media to another because it's changing speed. Diffraction is different. Diffraction, the wave is staying in the same media here. So you can imagine like this black and white stuff is the ocean, and this yellow line is just like a bunch of rocks. Well, the rocks are blocking most of the ocean from coming into the, say, this little inlet or whatever. Well, what's happening here is most of the waves that come in just bounce off the rocks, go right back out. But what's happening right here, that just a little bit of the wave passes through. And it doesn't just go through as just this tiny little sliver, it actually bends around it. You see how this almost looks like ripples in a pond, like if you dropped a rock right here. And the reason for that, that's called diffraction. It's the bending of a wave as it goes around an obstacle to try to fill in the space behind it. And so diffraction occurs with all waves. A great example of diffraction is looking at your shadow. Like if you have enough light for your hand to cast a shadow on your desk, you'll notice that the shadow only goes about this far. And if you're really close to your desk, the shadow is very sharp and distinct. But if you pull your hand up further and further, the shadow gets fainter and fainter, and eventually at some point, your shadow doesn't appear to be on the desk anymore. Well, it's the same thing like with a plane flying through the air. Most planes fly up really high, and the light comes down, hits the plane, and diffracts and bends around the plane. So it has a shadow, but it's only so long, which is why when the plane flies up really high, there's no shadow on the ground. Now, if the plane's low enough, yeah, you will see that shadow. And so diffraction is just the bending of a wave as it goes around a barrier. And so here, this shows you some invisible stuff. This one's pretty good. It has a good explanation of what's going on here. But again, you can watch that video on your own time. And then, again, this is the last slide we're going to cover today, is we have this diffraction occurring here where the waves are coming out and they're hitting the barrier, but this time there's two holes, so it will diffract twice. Well, when this diffraction occurs, it will bend around both barriers and it will interfere with each other. And so we'll have constructive and destructive interference, which is what we just talked about. And these areas here that you see, like the black, white, that, or black, yellow, I should say, not white. These areas here that kind of look like wedges, those are the areas of constructive interference. These things here, these kind of like spoke-like structures, those are the areas of destructive interference, where essentially the water is flat. And this occurs because both slits are diffracting, both holes here are diffracting, and so it's making two waves that will interfere with themselves. Okay? So